Everybody, we're very lucky to have Eli Waxman visiting from the Weizmann Institute, where he's a professor. If you're new to the field, I don't know if anybody is, but if you're unfamiliar with his work, just go on Google Scholar or ADS and scroll through the papers. It's kind of unbelievable the impact that he's had, and these are single, 2, 3 author papers. But today we're going to be hearing about an experiment. We're going to be hearing about ULTRASAT. Without further ado. And actually, let me just mention there are spots left for dinner, so please feel free to sign up.
Thanks for this opportunity to tell you about ULTRASAT, which is a wide field UV space mission that we are leading at Weizmann with the Israeli Space Agency, NASA and DESI. I'll say a few words about the project and the collaboration during this talk, but I will start with the science motivation that is driving this mission. So our goal is to study transient events, and there are 2 drivers behind the study of transient objects. One is the open questions. So there are many astronomical systems which are interesting and we would like to understand that produce transient emission, like the mergers of binaries that produce gravitational waves, the tidal disruptions of stars by supermassive black holes. And the systematic study of those, we believe, will also enable us to answer some open questions of wider importance, like the origin of the heavy elements beyond iron, or the distribution of masses of supermassive black holes at the centers of galaxies, particularly lower mass galaxies. Now, so these are and there are many more open questions in which we are interested. The reason that we believe that we are going to understand much better some of these objects is that technology now enables the construction of surveys with a very wide field of view, and this is necessary for studying transient events. So there are electromagnetic wide field surveys in the optical, radio, X-ray, gamma rays, and there are new gravitational waves and neutrino detectors with very wide fields of view that enable us to detect these transients not only in electromagnetic emission, but also probably in gravitational waves and neutrinos. Now, the UV is missing from this list of wide field observatories, and ULTRASAT is going to fill this gap. The main characteristics of ULTRASAT, which make it interesting, are its very wide field of view, 200 square degrees, and its UV sensitivity, which will reach 22.5 magnitudes in 900-second exposures. And this combination provides a very large volume that we can search for transients in. And this graph compares the RASC of ULTRASAT, the volume that is instantaneously accessible to ULTRASAT compared to other observatories as a function of wavelength, and it's normalized to 1 as according to ULTRASAT's graph.
What is it in real units?
Real units depends on the luminosity of the object that you're looking for.
Okay.
So you can always scale it together. So I'll show some numbers for particular types of objects later on. So as you can see, ULTRASAT is going to increase the grasp compared to current observatories by about 2 orders of magnitude, and it will have a comparable grasp to the Vera Rubin Observatory. And it will be observing at a wavelength regime which is not accessible to the other observatories on the ground. And being in space, it will provide a continuous cadence from minutes to months monitoring of the transients, which is not possible to achieve from the ground. And since we will be in a geostationary orbit, we would be able to disseminate alerts of objects that we detect in real time for the entire community to follow up. And finally, ULTRASAT is going to be also very agile, so it will be able to only point in the sky within less than 15 minutes from receiving an alert from another source. Okay. I will, increasing this grasp by 2 orders of magnitude is going to have a significant effect to the study of many transient objects. I will discuss only 2 of the ULTRASAT science goals due to the lack of time, and in a little bit more detail, and then I will make some comments about the other science goals. So one of our key science goals is to detect electromagnetic emission following mergers of neutron stars. As you know, these mergers are expected to eject relativistic plasma, which is highly neutron-rich, highly radioactive. And this is one of the prime suspects for the production of the heavy R-process elements. And the detection of the electromagnetic emission produced by this radioactively emitting plasma will enable us to determine whether or not this is the place where heavy elements are produced. It would enable the study of this ejector would provide constraints on the properties of matter at nuclear densities, on the dynamics of the neutron-star merger. And electromagnetic detection is crucial for localizing the events, which will both tell us in what type of environments the mergers occur. This will constrain the progenitor systems and also enable us direct measurement of H0. Okay, so detecting this electromagnetic emission is going to be one of the key goals of transient astronomy when the gravitational wave detectors begin to provide neutron star merger detection at a reasonable rate. And we believe that with 05, sometime late 27, the GW detector networks will provide some 10 events per year at a distance of 300 megaparsecs with a localization of about 100 square degrees. And ULTRASAT will be able to slew within 10 minutes one point on the sky. Its very wide field of view will cover the entire error box in a single exposure. And if the UV luminosity is anything similar to the one event that we have seen, we will be able to see these events to about 300 megaparsecs. Now, detections in other wavebands is going to be more difficult. I will not say too much about it. When we proposed the mission, this was well before 1708-17, and there were these arguments whether we should look for the follow-up for these kilonovae only in the infrared and so on. But I think that the 1708-17 gave a strong support for ULTRASAT. So this single event that was extremely close, 40 megaparsec, extremely lucky, was detected in electromagnetic emission, but it took about half a day to detect this electromagnetic emission because the error box was pretty big, and narrow-field telescopes were searching galaxy by galaxy looking for the transient emission, and this took about half a day. And although it was a bit late, it was still extremely bright in the UV. We expect the UV luminosity to be brighter at the earlier times. And it was very faint in X-rays, as we suspected. So detections in other wavelengths of such events at 300 megaparsec is going to be very challenging. And ULTRASAT will be able to do this, I think, best. One of the issues I will not get into, from this event, we know that indeed heavy elements, unstable radioactive elements were produced, but what the composition was is still highly uncertain, and early UV measurements at early times would also be very important for answering this question of the composition. So if you compare ULTRASAT to other observatories like VRO, you see that, assuming that we have something like 10 events per year, ULTRASAT will be able to detect more than half of them within 3 hours, but all the others will be having a quite a difficult time doing this. And the other histograms show our capability for detecting supernovae at early times, which shifts me to the next key science goal. So ULTRASAT will detect hundreds of supernova earlier than 1 day following the explosion, and tens of supernova per year within an hour from the explosion. It will provide continuous, accurate UV light curves and early alerts for other observatories to take spectra and multi-wavelength observations. And this will enable us to do many things. One is to determine the progenitor parameters. So what you see here on the right top plot is the early UV emission from different type of progenitor explosions, red supergiants, blue supergiants, Wolf-Rayet. And you can clearly see that UV measurements allow us to discriminate between these objects. These are serendipitous detections by Swift, which mainly tell us that we can rely on the models. And this is simulated UV light curve from ULTRASAT. And with one additional band from the ground at much lower cadence, you can see that we'll be able to determine the radius of the progenitor to like 20%, and the explosion energy to a similar accuracy, which is not possible to do by any other method. And the fact that we will have detections of hundreds of those implies that we will also have significant number of events detected from the rarer blue supergiant and the Wolf-Rayet type progenitors. So this will enable us to do a complete mapping of the supernova explosion types to the progenitor types. The early UV measurements will enable us to determine the mass loss history of the star. We'll not get into this. We know that many progenitors do have significant enhanced mass loss during the year prior to the explosion, and the early UV measurements will be able to measure this, and we will be able to determine the extinction of these events. So all this is going to give us a lot more new information on the progenitors of the supernovae.
And also the breakout, right? Because there was once a detection of a breakout in the UV. Long time.
Right. So this 1 hour time scale is the breakout time scale. The day time scale is sort of the cooling envelope time scale. So we'll have tens of breakouts and hundreds of shock cooling. There's tens of breakouts. This part is more sensitive to the mass loss history of the object. And, yeah.
I'm not understanding why. I appreciate the UV is uniquely important, but I'm not understanding why LSST is not able to find examples of 1 hour things. Is the issue that because they're always moving that they don't sit in well and actually characterize the objects that they found?
Right. So their observing strategy is such that it will not enable them to detect these very early transits.
Yeah, they're tiling the sky.
They could do much better if they modify their observing strategy, but they are unlikely to do this.
By chance, they'll find some examples of 1 hour, but it's just that they're not giving any.
But they're also
Yeah.
bright in the UV.
Yeah,
By chance, you see this. By chance is like once per year, or less, due to their observing strategy.
There's also, so recently, people have been thinking about these stripped envelopes that have these pseudo kind of photospheres that the shock can break out of, like the 1BNs, the 1CNs, the 1ENs now. I'm wondering if you've thought, like, what are the expected rates of seeing breakouts from there and getting measurements on that CSM?
So, okay. All these estimates do not assume this enhanced CSM.
Okay.
If we add it, the luminosities are going to be higher,
Yeah.
so the rates would go up. By how much, I don't know, because I don't know what the statistics of these muscles is. Although we do have some indication, and this is this slide. So we have some proof of concept for how well we will be able to do with these measurements. So this is a sample of some 34 type 2 supernova, which were detected at early times with ZTF, and had some fairly early, few days, swift UV follow-up. And what you see on the left is an example of this many wavebands observations and the fit to the simple cooling envelope models that reproduce the data fairly well, from which we can determine the radius. This type of fits is characteristic of, let's say, half of the sample. Half of the sample is not well fit by these models. There are some early data points which do not fit, and this is probably due to the presence of CSM. So I think we have some evidence that for normal type 2 supernova, like half the progenitors have significant CSM around them, and this would increase the UV luminosity, increase our rates. And with ULTRASAT, we'll have accurate measurements at this time scale, and we will be able to map the massless history of these stars. Okay, I need to move on because we don't have much time. So I talked about two of the key science goals of ULTRASAT. There are many others. I will mention that ULTRASAT will monitor hundreds of thousands of dwarfs, and we'll be able to map accurately the UV activity, which is important for planet habitability. We will have continuous monitoring of about 10,000 AGN in the UV that will enable us to do much better aberration mapping with the UV, which is due to the inner part of the disk. We will detect thousands of TDEs, which will enable, for the first time, to systematically study these events. And there are many more science topics to which ULTRASAT will bring, I think, a major impact. Some words about the mission. So at the beginning, we will do an all-sky survey. 10% of the time will be dedicated for creating a full sky map. Most of the time, we'll be staring either in the north, near the north ecliptic pole or the south ecliptic pole. This is where we have the least extinction and the least zodiacal background. We will devote part of the time for a lower cadence wider field, about 10,000 square degree with about 1 day cadence. And as I mentioned, we will be able to swoop any point in the sky within less than 15 minutes from receiving an alert. And
what does the greater than 3 hours mean?
We will be able to stare in any point in the sky for at least 3 hours. Some positions in the sky, you don't get sunlight on your solar panels. So this limits your ability there. So this is what we call hard TOOs, but the minimum the time that we will be able to dwell at any point, even without any power, is 3 hours. This is how ULTRASAT would look like. This is the telescope with a very long buffer. The stray light rejection constraints are very stringent, so we have this huge buffer. And the buffer is also shielding from cosmic ray electrons that would hit the outer lens of the telescope and produce strength of light in the UV, which would increase our background. So it's a curious thing for the UV. At the center of the telescope, there's the focal plane array. The telescope is produced by ELOP, which is an Israeli company, according to the Waxman design. The focal plane array is the contribution of the DESI partners. And the sensors, especially the sensor, I'd say one of them have already been produced by the Israeli company, Tower. And the satellite is constructed by IAI, which will be also responsible for the complete integration. NASA is providing the launch to geotransfer orbit, and we plan to launch at the end of 2027. You see here the characteristics of the mission. So most of the weight is the fuel that is required to circularize the GTO orbit to geosynchronous orbit. So otherwise, it's a fairly small sample. 600 kilograms of fuel. And the mission lifetime is going to be 6 years or more. I do not have time to discuss the technology and the different challenges that we had in constructing the mission. I will just say one thing about the sensors mainly. So one of the key requirements for being able to achieve this mission is to have high quantum efficiency detector. And until recently, it was not possible in the UV. The typical efficiency was a few percent. Our detectors are more than 60% efficient in the around 250 nanometers. This is achieved by a combination of special combination of coatings that prevent UV reflection and dielectric coating that prevent charge accumulation on the surface where the UV photons are absorbed. So you can see the specs here. As I mentioned, this was one of the major challenges to the mission. The sensors have been produced and tested, and they meet all the requirements. This is to show you that this is a real mission. This is the bus of the satellite that already sits at the IAI. This is not the flight model, but this is the demonstration model. These are real sensors that have already been produced, and this is the four mosaic sensors. We separated this detector to 4 parts so that if each part is for some reason malfunctioning, the others continue to work. So we have a graceful degradation. This is the mirror that has already been produced at ELO. So overall, we are, I think, well on track. All the technical risks have been, the major risks have all been removed. All the long lead items have been purchased and are either at the factories or on the way to the factory. Everything will be there by the end of this year. The constructions of the different parts have already started, as you saw. The main challenges that we have now is to carefully monitor the complex interfaces between different nucleus and the contamination, which is a major issue for UV emission. Any organic molecules that are emitted by glue or whatever is being used to construct the satellite could attach to the lenses and to the sensor. The sensor is much colder than the rest of the structure, and UV absorption is strong, so we need to monitor both during the construction, the integration, the launch, and also then after launch, the accumulation of contaminations. The total mission cost, excluding the launch, is about 100 million, which is a very low cost compared to other space missions. This is one of our challenges, to prove that we can do all this in a relatively low cost. One aspect that I don't have time to discuss is the science. Yes.
Quick question. So with the sensors that you talked about, is the PSF undersampled?
Yes, we noticed that, right. So our PSF, our average PSF is about 8 arc seconds, and there are some regions where the PSF scale is 5 arc seconds. So yes, part of the field is undersampled. And this is a good introduction to this slide of the Science Operations Center. So there is a big effort, not only for the construction of the satellite, but also for the construction of the data center, the pipeline, the analysis. And this is all done at Weizmann. The data center will sit at Weizmann. That's where all the data will go to. That's where alerts will be issued from, and that's where we will command the satellite to call out alerts. One of the challenges is to develop optimal algorithms for co-adding and subtracting images with undersampled pixels. This is also one of the things that we are currently doing as part of this pipeline development. What about science collaboration? So the alerts, of course, will all be public. Transient alerts. The rest of the data will be proprietary for the working groups for about 12 months, so they can do a proper job on everything. There are 13 science working groups of ULTRASAT. the working group members will have access to all data in real time. The US received 14 PIs in return for the launch that NASA provides and for the collaboration that we have established with Rubin. They received 6 US PIs in return for making the Rubin data accessible in real time to all the Israeli astronomers. Our DAISY partners received 3 PIs. All the groups have already been formed and they are working. They address different lines on this table that I've shown you of science notes. There are some other collaborations which are emerging. The Czech will be launching a small satellite with a narrow field of view with 2 UV bands below and above the ULTRASAT bands to follow up ULTRASAT targets. The Liverpool 2-meter automatic telescope at Parma will devote a lot of large fraction of its time to follow up ULTRASAT targets. And we are developing also our own follow-up capabilities. The leadership of Sagi Binami, Ranofet, and Avishai Galyam. Our own observatory in the Negev Desert in Israel, which would have both spectroscopic and photometric follow-up capabilities, and with our collaboration with other observatories, we would have a wide suite of follow-up capabilities. Okay, so just on time. I think ULTRASAT will revolutionize our ability to do transient studies, increase the volume accessible to transient detection by 2 orders of magnitude compared to what's available today, provide continuous cadence, minutes to months timescales in the UV band with high sensitivity, and it will provide real-time alerts to all the community to follow up the transit that we detect, and we'll have the capability to swim fast to follow up transit detected by other observatories. It would have a broad impact on many transient astronomy subjects. I've mentioned gravitational waves, sources, and the supernovae. I didn't mention the flaring stars, PDEs, AGN, compact objects, also galaxies. And it will be doing all this with an affordable cost of about $100 million for the mission that's being launched, which proves that you can do groundbreaking science and space missions at the scale that small states like Israel can actually afford.
Okay, questions, Avi?
First, a comment. Obviously, these are sources we know about, but the most interesting discoveries will be things we are not aware because you are increasing the volume you can. But my question has to do with background, because if the satellite is put in geo, is there any glow from the atmosphere or the magnetosphere of the Earth that is an issue, or anything of that nature?
Yeah. So for the first comment, you're absolutely right. Maybe the things that I'm discussing will be the most interesting things that we'll certainly find. We will see. One of the things that we know that we map much better than we know today is this region of F-bots, the fast growth optical transients.
Sorry, can you elaborate? F-bots?
F-bots, fast blue optical transients. So these are like weak, fast supernovae, maybe. We don't know exactly what is producing them. I think Ashley can talk about this. And we will map this region of our space. But maybe there will be other interesting things. Yeah. For the background, so our main background is the zodiacal light from the disk of our planetary system. There is the second contribution to the background is the Cherenkov emission from high energy electrons, which are confined by the magnetic field that penetrate our detector. So these are the two leading background sources. We of course are limited. We do not look at the Earth or at the Moon because they do produce. So the atmosphere is oxygen 247 nanometers. So we do not look at the Earth atmosphere. We do not look at the Moon. But apart from that, we're very limited by the light and which information we get.
I have two questions. One, just a quick one about whether you're flying as a primary or a secondary payload at this cost cap.
So the NASA would issue a tender for launch about 2 years prior to the mission. So this would be early 2025. It is likely that we will be primary. It's most likely we will be the primary, and then the secondary would be searched for after we are selected, after the launch has been selected. The so-called LSIOD, this little document that manages the interfaces between the satellite and the launcher has already been set. That's some issue. So the launcher would be would need to meet the ULTRASAT requirements, and then the secondary would have to meet those requirements as well.
Okay, thank you, that's good. That's really good.
Yes, well, that's very good. We already had one disaster with the NASA launch, which is initially they promised that the direct launch to GEO, and then they shifted to GTO, which caused a year delay and $50 million increase in the cost because we had to add this propulsion system and huge fuel tank to the satellite. Okay, so we already had our disaster one, and I think now everything is settled, the other side is fixed. I hope it don't happen.
I hope so too. A science question. There's many practical reasons to choose the NUV for sure. Scientifically, for your two key science cases, what would you gain if you had the far UV also? If any.
It would be, so in principle, we would have liked to go to even shorter wavelengths because these objects, essentially these objects are very hot, and we want to see the UV emission, we want to determine where the temperature, and so it would be, and the background is lower, so it's better to go to shorter wavelengths. The reason that we went only down to about 220 is because when you go to shorter wavelengths, because of the very strong dependence of the refraction index on the wavelength, it limits the range of materials that you can use for the lenses, and you need to use sort of much more exotic material, and so everything becomes much more expensive, and it will not use in our cost cap. So that's why we stopped it.
Is that true even for a very narrow wavelength range? Like the difference in the refractive index is so steep that.
Yeah. So if
Okay.
so the real issue is actually the very wide field. So if
okay.
you do a narrow field, then the strong dependence is not so crucial.
Not a big deal, right?
It's not a big deal. If you do a very wide field and you want to keep a reasonable PSF across the wide field, the strong dependence speeds you.
Okay.
So for this Czech satellite, for example, it is a very narrow field of view. So it would go to shorter wavelengths and would follow up ULTRASAT at shorter wavelengths. And also, like for Swift, for example, Swift will probably also follow up ULTRASAT targets, much more field of view. And it does have a band which is shorter wavelengths.
Okay, so it's the other way you can solve that same problem without getting out of control. Yes, understood.
But since ULTRASAT is about detecting a large number of transits so that you can do systematic study, so we need a very wide field of view, and that's.
Other questions?
This is a small question, but what are the brightest sources in those high cadence fields that are unsaturated?
So the brightest sources are the galactic stars.
Yeah.
We'll have several hundreds of stars which would saturate the ULTRASAT detector at this 900 second.
So it's like a magnitude of a few
Yeah.
is unsaturated.
Right.
Okay, interesting. Because I think those 5-minute cadence data sets for so many of those stars would be amazing.
Yeah, right. Some of these stuff will be separate.
Few will be separate.
Few will be separate, yeah. And so, yeah, we have this, in developing the pipeline and the image subtraction capability and the field flattening capability, and of course, we rely on stars that were well monitored, measured by Hubble, which have good spectra of UV. This we will be using for calibration and for flat fielding. And we have a sufficient number of them which are not saturated to do this. If we need in any fields. Yeah. So there's a lot to be said about these issues.
Yeah.
So I have a question about alerts.
About
Alerts. Do you produce alerts for negative flux?
for negative flux.
Yeah.
You mean a drop in flux?
Yeah, something that disappears rather than appearing.
Okay, it's a good question. So we will be monitoring white dwarfs for UV planet transits. So in that sense, we will be looking for negative alerts. But in general, I don't think we thought about, just in the field, looking at negative alerts. Okay, maybe this is something we should think about. Do you have some specific
Collapse to a black hole.
Yeah, something like that.
star disappearing
Yeah.
in a nearby galaxy?
Yeah, because people talk about like massive stars, the electric flux into black holes, so they should be blinding UV, and they could just disappear with that.
Just disappear.
What would be the benefit of a rapid follow-up?
It's not the time
It's the
scale,
sensitivity.
but just searching with this sensitivity. as
Yeah.
they
Oh,
were
yeah.
done before.
Oh, so you'd have that data in your survey, but it wouldn't necessarily cause an alert
Yeah.
as far as a rapid response requirement.
Yeah, I guess, and
But there can also be like a low luminosity optical transient that you can follow up. It might be.
So, yeah, we will be monitoring any variation. Right? So we will identify any variation. What we will issue alerts on is good. We will definitely detect those things.
yeah,
But the question is, do we issue alerts about them? So we will issue alert if we think there's something worth for the community to look at fast. Right? We don't want to issue alerts that people would follow and then say, okay, it's not justified to invest resources and so on. Okay, but maybe we should think about this. Some things that do deserve real-time alerts. If you have some ideas, you can send them.
yeah.
Yeah, going to geo is an expensive thing to do in terms of the mass you can fly at, so, and needed fuel and so on. So I wonder what was the main driver that made you all opt for that? Was it the data rate down? Was it the continuous link? Was it the field of regard? Or?
Yes, and yes.
Oh, yes, yes.
And more. So, yeah, so one thing you already mentioned, we want to have real-time connection, both for downloading alerts and both for uploading a new slew of positions. We don't want to have any delay, so this is one thing of the geo. The other thing is the air glow, 247 nanometers, which I already mentioned. There's a strong oxygen line there, which increases your background dramatically, so you either need to do two bands around it, like UVEX, there's Caltech JPL mission, we have two bands around this 247 nanometer line. And the field of view. We want to have an absolute field of view. We want to do in 10 minutes any point in the sky, and if the event happens to be in the best location compared to Earth, it's also will get better work. So for all these reasons,
Are there any plans to repeat the all sky survey at any cadence, like even if it's years or a year, every year?
to do another also survey?
Yeah, the reason I'm asking is because there's this population of supernovae that show late time CSM interaction with UV emission, and people have just done like HST snapshot surveys to find this type of thing, but they're there. And I suspect these will show up in the near UV, even if you do a very slow survey of the whole sky.
So I think this will be addressed by the the lower, so we have two modes, right? One is the steering mode, which is 200 square degrees with 5 minutes cadence. And the other is this 10,000 square degrees with a day cadence. So I think the second lower cadence survey would answer your question. Because we will have very deep images of all these 10,000 square degrees that we monitor. So I don't think we need to do another full sky survey for that.
Can I ask a question about UVEX? So UVEX will launch 3 or more years after ULTRASAT. Are they distinct enough that they'll end up just complementing one another, or will you get to a lot of UVEX science first?
Yeah.
That's a political question.
I know.
Yeah, there's a lot to be said about the history of ULTRASAT in the US, but privately.
Okay.
So there are some different. Let's start with the differences, with the technical differences between ULTRASAT and UVEX. UVEX has a similar grasp to ULTRASAT, so the volume that they see is similar to us, but they are much narrower field, like more than 10 times narrower field. So they look much deeper into the universe, and they have similar volume. The implication is that even if they detect transients at a similar rate, most of them will be too far for spectroscopic follow-up. So one of the reasons that we chose this combination of 200 square degrees is that most of our events would be at a distance that would allow follow-up and spectroscopic follow-up and so on. So this is one difference. The other difference, they also have a spectrograph. They are a bigger mission, right? It's a meters.
Yeah.
So they also have a spectrograph which we don't have, which is important. And last thing, because they will be in this elliptic orbit, they would have 6 hours latency. So for real-time alert distribution and for real-time slewing, ULTRASAT would be much superior. So I think that there would be after UVEX is launched, there would be a good cooperation. I think we already discussed this for UVEX to follow up ULTRASAT targets. So we would have this wide field detecting nearer objects that could be followed up by UVEX, and we will have such a collaboration.
Thanks. Any more questions? Okay, let's thank Eli again.
תגידו.
It's a really clever mission. Because going to geo is counterintuitive for most mission people.
Excited to hear the story.
Okay.
Hi, so this is Kishore. I'm very familiar with this. The reason I asked for the PSL question is because I worked with Eran Waxman when I was a grad student at Caltech with Mansi. And then I spent a month at Waxman when I was in grad school working with Eran, on exactly this problem.
So where are you?
Yeah. So we were working on this exact problem of doing image subtraction with undersampled PSLs.
So our real problem now is that we know how to do this if there is no rotation. Our problem is that there is a rotation between the image, so we'll take the whole sky map, and then we will go back to some point, we will not be observing it the same orientation.